So hello, everyone. Today I'm going to talk about a method to assign value to data called data Shapley. And this was a work done by James Zhu and me at Stanford University. But before I start, let's think why assigning value to data is necessary. What's the point of assigning value to data? Now, looking at the different groups, different stakeholders that work with data or are related to data, we have three main groups. It's either that you are the person working with data, you are a machine learning engineer, a data scientist, and in a real-world setting, your data is coming from heterogeneous sources, from different people, different companies. Now, you want to take into account the differences of these different sources. Or you are a data vendor, and your most important question is how much you are going to pay or how much you are going to sell your data. What's the price of the data? How much are you going to pay to compensate people that gather the data for you? Or most importantly, and recently the most hyped one basically, is to compensate individuals for their data. And very recently, the governor of California asked for this, to compensate people for the data they basically consciously or subconsciously give to companies. But our focus in this work is on data valuation for machine learning, and we try to have the fewest assumptions, the simplest assumptions. So all in all, machine learning can be boiled down into three ingredients. You have a trained data, which we have shown here by 3 data points or data sources. I'm going to be using these two terms interchangeably, so data point or data source. We have a learning algorithm, and the way we look at learning algorithm is just a black box that takes the training data and outputs a predicting model, a trained model. And the last one is the performance evaluation, which is again another black box that given a trained model gives you its performance. So it's either test accuracy, F1 score, or even the revenue that model generates when you deploy it. So the goal is, given these 3 main ingredients of machine learning, can we divide the value of the model, the value of that data, which is its performance, among those sources of data? So for instance here, the trained model on this data gets a performance of 0.8. Can we divide this in an equitable way between the 3 sources or 3 points of data? So again, the valuation we're going to have is going to depend on these 3 ingredients: the data itself, the learner, and also your performance metric. But the main question is, among the infinite ways of assigning value to data, of dividing this performance among these data points, which one is the right one? So to start with, let's talk about one very intuitive method called the leave one out method, which most of you know about. So let's say in this simple example that we had, we want to assign value to the data point star. We want to see what's its value. So its value is going to be basically its marginal contribution. So what will happen if I don't have that data point, if I remove that data point? So as you can see, the performance is 0.8, and when we remove that data point, it becomes 0.77. So we assign a value of 3% to that data point or data source using the leave one out method. However, the question is whether this is the right valuation we are looking for. Is this the reasonable valuation method? And to answer that question, we have to first define what we want from a reasonable valuation method. So I'm going to be talking about 3 properties that we'd like to have. These are definitely not, and we do not claim these are all the properties, but probably these are the most intuitive properties that you must have. So the first one is the null element property. So it kind of relates to what data does not get any value. And the intuition behind it is that if one of your data sources or data points never changes anything about your trained model, and its manifestation is if you add it to any possible subset of the rest of the data, the performance is not going to change. This is just an element that does not change anything. Its existence doesn't matter. It's going to get 0 value. The second one, which is more related to being equitable, to being fair, is that if you have 2 data points or data sources that always give the same amount of change. So if you pick any random subset of rest of the data, and if you add either of these points, the change in performance is going to be the same. So these are basically 2 data sources, but they act completely the same as each other. So it is fair to assign equal value to these two. The last one is actually quite a specific one for machine learning, an interesting one. So in machine learning, many times, the performance metric you use is a sum of individual performance metrics. So let's say you have test loss, and your test loss is just a summation, a linear combination of individual test losses and individual test points. So we want to keep this linearity in our valuation too. So for instance, let's say you have 100 test points, and you perform valuation for your training data. Now you add another 100 test points. So instead of beginning from scratch, we want the value for the first 100 test point and second 100 test points added to each other to be equal to the case where we combine these two and assign valuation. So we want to keep linearity of performance metric in our valuation. So going back to the question, does this valuation exist? And the answer is yes, and it is unique. So this is how it looks like. If you have n data points or data sources, this is how we should assign the value of the kth one to satisfy the properties. And going through this formula, it's basically this. So assume S is just a subset, any subset of the training data that does not contain K. So remove K from the data and pick a subset from the rest of the data. And add K to that subset. Look how much it contributes, what is its marginal contribution to that subset. Then normalize this value by the number of all the subsets of that size. So number of all the subsets of size 10 among n-1 possible data points. Then sum this value for all the possible existing subsets. In other words, the value we assign is basically what is the expected contribution of data K if it could be added to any size of training data. So let's say right now you have 1,000 points, but you could have had 10 points, or you could have had 20 points. What is the expected contribution of this data K if it could be added to any of these sizes of data? Now, going back to our simple example, again, we have these 3 data points, 3 data sources. So the rest of the data is just 2 other points, the hexagon and the pentagon. So there is only one size 2 subset of data. There are 2 size 1 subsets, and there is only one size 0 subset. So there are like 4 different marginals for data point star. And after normalizing these marginals, we just sum them together, and you get value 0.05. Now, the biggest drawback with this evaluation method is that it needs exponential number of computations in the size of your training data. So what we did in our work is that we developed efficient approximation algorithms to be able to compute these Shapley values of data. So basically, the data Shapley that we have here is a direct consequence of Shapley value introduced by Lloyd Shapley for cooperative games. So in a cooperative game, you have n players, and they come together to cooperate, and the whole group gets a value. And the Shapley value tries to divide this group's value among individuals such that it's fair. Now, the case of machine learning is exactly the same thing, but people, instead of bringing their labor, are not bringing their data. And in the end, this cooperation of data gives you a model that has a performance, that has a value. And data Shapley basically divides this value between individual sources of data. So this is basically kind of, we're done. We have a method that satisfies the desired properties of valuation. But as machine learning people, we want to see, are there other machine learning applications of this value? So apart from being equitable, what can we use this value for? So again, going back to the formula, a data point's value is just its expected contribution to performance. Now, if a data point has high value, it means that it's expected to add significant information. So it could be a data point that is clean and inside distribution and everything good. But the reverse case is a data point that has negative value or low value, which means that it's expected to always contribute negatively or none to the performance. So it can be noisy data, it can be outliers, it can be mislabeled data. So if we have data points that are harmful, that are of low quality, we expect them to be of low value. So the first application we are going to talk about is using data valuation to see whether we can discover these harmful points, whether we can detect them. So the first example is spam classification. So let's say we have a naive-Bayes model, and we flip the label for 20% of data. So there 20% of the data have incorrect labels. So if you want to inspect the training data randomly and correct these flipped labels, you have to go over all the data. However, if you start from the least valuable data points, you can almost discover all of them after checking 20% of the data. In other words, the mislabeled data points are all among the least valuable data points, as expected. So the second application is kind of the reverse case, high-value data. So for this experiment, we use the UK Biobank data set. So UK Biobank has the information, phenotype, genotype of 500,000 individuals in UK, and it's gathered from 22 centers. And we can transform these 22 centers and look at each of these centers as a player, as a data source. And if we do that, we can divide the value between these 22 centers. So what we did, we created binary classification tasks, balanced binary classification tasks for disease prediction, and then we tried to divide the value of the trained model among these 22 centers. So this is how it looks like. The figure on the left side shows the number of patients in each center. So centers have different number of patients. They contribute differently to the size of the data. And the two other figures show the value each center gets for each of these prediction tasks. So if your task is predicting whether someone is going to be diagnosed with breast cancer, for instance, source 12 gets the highest value, although it doesn't have the most number of patients. Now, if you want to predict colon cancer, center 15 is going to get a big negative value. But we looked at what information we can get from this valuation. So looking at the case of colon cancer prediction, you see that center 15 has a very negative value. And it can either be that the data quality is low or something else. And we hypothesized that it's due to this distributional difference. So when we train a model for predicting colon cancer, age is the most important feature. And the older you are, the higher chance you have. But this center, specifically, age is unrelated to having cancer. So this distributional difference might be the reason that it gets a high negative value. Although it has a lot of patients, it contributes a lot to the data set size. Now, another question is, let's remove data points. And if we start removing data points randomly, the performance will decrease, as expected, because the training data size is becoming smaller. However, if we start removing data points from the most valuable ones, the situation is very different. So you can remove half of the data point. If you do that randomly, the performance doesn't decrease that much. But if you remove half of the data that is the most valuable part, performance becomes worse than random. So data points that get high value are actually crucial for models' performance. The reverse case, adding data. So let's say we are given a pool of new patients that we want to choose and add to our data. And as a real-world setting, we don't have money to buy everyone's data, so we can buy half of the data. So if we add patients randomly, the performance increases. But if we try to find patients that are similar to our high-value data points, to our high-value patients, the increase is much more. And the last case is domain adaptation. So the pipeline doesn't change. We again have a training data, we again have a learning algorithm, and we again have a performance metric. The only difference is that the training data and the performance metric use two different data sets, two different distributions. They're either different in quality, distribution, class balance, and et cetera. And the question we want to ask is that if we calculate value for data points in the training data, is it going to be the case that some of the data points are very useful for the task of adaptation, and some of them are not useful? Are there data points that help a lot with adapting to this new data set, or data points that just harm that? So the way we try it is that we remove data points with negative value, the harmful data points, and we reweight the remaining positive value data points with their relative value. So data points that get very high positive value are emphasized to have more contribution in the training task. So as a simple experiment, The target data is HAM10,000, which is a data set created by clinicians. So it's very expensive. The task is to detect skin lesion, 7 different lesions. But our training data, we sat down and just did Google image search. So it took like 4 hours to create. So as you can see, our training data is very unclean and noisy. But it has a few images that are related to the target task. And this is a very similar real-world case where you want to gather data from Google image or et cetera and just adapt to a new data set. And after doing this, after removing negative value data and reweighting positive value data, as you can see, test accuracy increases around 8%. So relative performance increases around 25%. The last experiment is, again, domain adaptation, this time for gender detection. So it has been shown that for benchmark data sets, the performance on minorities, and specifically women, is worse than majority groups. So these are 2 very famous benchmark data sets. LFW plus A has around 80% male, 95% white. PPB is specifically designed to have equal representation of all skin colors and genders. So when we train on LFW and test on PPB, the performance decreases. But when we do domain adaptation, with this method, we can see that the performance increases. But the most interesting part is the 20% high-value data points are all female. The 20% low-value data points are all male. So the Shapley value of data points that are important for the task of adaptation is more than the ones that are harming the adaptation. And one of the algorithms we used for approximation is TMC Shapley, truncated Monte Carlo Shapley. And its idea is simply approximating that exponentially hard computations of Shapley value with Monte Carlo estimations. But being in the setting of machine learning, we can add another level of approximation, which is truncation. And we can talk more about this at our poster. So in general, we developed a valuation method that is equitable, and we showed 3 main applications of it. Thank you very much for your time.
Hi, everyone. My name is Regularizer. I'm an assistant professor at Stevens Institute of Technology. This is a joint work with my collaborators, Bertrand Thrion and Gail Varoqua from INRIA, France. So high dimension and small sample data situations are common in fields such as brain imaging, genomics, seismology, astronomy, chemistry, etc. And fitting complex models in these situations can be challenging because, first, the feature dimension can be large due to rich temporal and spatial resolution. Second, there might be noise in the data due to the artifacts unrelated to the effect of interest. And also, the sample size is typically small in these situations due to logistics and cost of data acquisition. So regularization strategies can address some of these issues. This is a really rich field, and I will only mention the works that are most relevant to ours. So pooling layers in convolutional neural networks can improve generalization, and the main idea that they depend on is the translation invariance. For example, a cat should be identified as a cat whether or not it is shifted to left or right. But this cannot be the case for some fields, such as medical imaging, because let's say your liver is not in your head, so it can be translation variant. And group lasso uses structure and sparsity, but the problem with group lasso is that you need to manually define the groups of features. And dropout depends on the stochasticity, and it's a cheap way of ensembling models. So in our proposed work, we use both structure and stochasticity. So in order to capture structure, we use feature grouping, and the algorithm that we use is recursive nearest agglomeration, or RENA for shorthand. So RENA is a data-driven graph-constrained feature grouping algorithm. So the way it works is that each feature, or a pixel, if it's an image, is assigned to a clusters, and clusters are then recursively merged until the desired number of clusters remain. So there are 2 advantages of RENA. First, it's a fast clustering algorithm, and second, it leads to good signal approximations. Once we train RINA, we can define a feature grouping matrix phi, which is k by p dimensional, and k is typically much smaller than p, and it's a sparse matrix. And for this feature grouping matrix, each row can actually capture a different structure in the data set. And once you have this feature grouping matrix, you can represent your data in the reduced dimension by just multiplying your input with this matrix. And you can also define your data in a low-rank approximation using this matrix again. So for our proposed approach, let's start with a fully connected neural network with H layers. And we represent this as theta, where W's represent the weights and B's represent the bias terms. And now we generate feature grouping matrices where each is generated by randomly sampling, say, R samples from the training data set with replacement. And we sample a mini batch of M samples, and let's assume our M sample is equal to 1 in this case. And we randomly pick a feature grouping matrix from our bank. And we redefine the parameter space, which is different than the original parameter space only in W0, and we complete the forward propagation. And we do the backward propagation, and we compute the gradients in the lower dimensional space. And to update the W0, we project the gradients back to the original space, and other terms are treated in a standard way. So our results show that our approach is computationally efficient and robust to noise, and it also performs best as the sample size decreases. For more, please come to our poster tonight with number 121. Thank you very much.
Good morning, everyone. My name is Sen, and today I'm going to talk about metric optimized example weights. And this is a joint work between Monte, Harry, Maya, and I in Google Research. And let's start with a motivational example. Suppose we want to build a ranking model and to rank some kind of, like, for example, documents or search pages. And the metric we care about is precision at 3. And we want positive precision at 3 globally. But we don't want to sacrifice the user experience in one locale for the user experience in another locale. So specifically, we also don't want to have negative precision at 3 in any specific countries. So we collect some data. The training data is from January to October, and the testing data is from November to December. So they are well separated. And we train the model, ranking model, with pairwise hinge loss. So the first attempt, we trained just a ranking model on the global data, and we get the result. The result shows that we got good global precision at 3, but the metric is negative in Japan and Brazil. So this may suggest that the Japan and Brazil data are underrepresented in the training data, so we should upweight them. So we tried attempt 2. So we upweight Japan and Brazil training data, and now we get good metric in Japan and Brazil. But now we get negative result in UK and India. So we do this again. We upweight UK and India training data, and now US turns negative. And this is actually the struggle that lots of practitioners face. That is, there are two issues here. The first one is the training distribution actually does not match the test distribution. The training data comes between January and October, and testing distribution is in the holiday season. And more importantly, our training loss does not match the testing metric. The training loss here is the pairwise hinge loss, but the testing metric we care about is precision at 3. So lots of practitioners face this challenge, and then lots of proposals are trying to address these challenges. And here we propose metric optimized example weights, and we call that MEOW. And our proposal actually learns the optimal weighting on training examples to maximize the testing metric. And our proposal is actually suitable for any loss, regardless if it's square loss, logistic loss, or pairwise hinge loss. It's suitable for any metric. It could be a black box metric, it could be a non-differentiable metric, and it's also applicable for any model class, regardless if it's a logistic regression model, linear regression model, tree-based model, or deep learning model. We also provide theoretical analysis in the paper, such as the generalization bound. So under the hood, actually the MEOW incorporates 2 models. The first model is the main model, which is just a typical empirical risk minimization problem with weighted loss. And here the W term is the weight, And the L term is the classical loss we use, such as square loss or pairwise hinge loss. And the MEL also uses another model, which is the weighting model, W. W has one parameter alpha that is learned to maximize the validation metric. And you can see that here. And the M hat is actually observed metric. And XV and YV are actually the validation data, validation features and validation labels. And the theta hat is actually the main model parameter. So we learn the main model and the weighting model iteratively. So here's a sneak peek of our proposal MEL. And for more details, you can refer to our paper or come to our poster. So this is actually a plot, a two-dimensional plot on the weighting space. So our weighting model depends on two features, the X feature and the Y feature. And the dots are actually the weighting parameters that we optimize in the MEL procedure. So at the beginning of the step, we try those weighting parameters basically randomly and uniformly across the weighting space. But as we go on, you can see our weighting model converges to the bottom right corner. That basically means we should upweight those features, those examples with larger X feature and smaller Y feature, like this. And as the training goes on, you can see at the beginning, this is the test metric. At the beginning, our test metric is actually lower and very noisy. But as the training goes on, the MEL training goes on, our testing metric converges to a high value. And for more details, please come to our poster tonight between 6:30 and 9 p.m. at Pacific Ballroom number 122. Thank you.
So I'm interested in model evaluation studies, but of course, before we can do model evaluation, we usually do some training of different models by means of different learning algorithms or hyperparameters or both. And then what is often recommended is to have some validation data set, as we just heard, to perform model selection. Basically, the most obvious choice there would be to maximize the empirical performance, for instance, the empirical accuracy on this validation data set. So in the end, we have our final prediction model. However, in particular, in regulated environments, we usually want a more reliable assessment of the performance of the final prediction models. So for instance, that is common practice in medical testing applications, where I'm interested in. So as hinted, the usually recommended strategy is select one final model and then do sort of an evaluation study, which looks very simple. We have some test data, again, independent data, where we can do some performance estimation. We can compute a confidence interval around that estimate, and we can do some statistical testing for decision making. However, this approach has a severe drawback. Namely, if we find out in the evaluation study that our model is not performing as expected, we cannot just go back and change our model and hence our hypothesis, at least if we want to do strict statistical inference. So in order to overcome this issue, what we are proposing basically is to account for the selection uncertainty and allow for the selection of multiple models for the model evaluation, which might look like this. Now we have multiple models here in the end, and our evaluation study now also looks more complex. Basically, we're assessing the performance of many models together on the same data set. And in order to do that, without introducing over-optimism, we need an adjustment for these multiple comparisons which are taking place. And we employ a specific parametric approximate procedure based on the multivariate distribution of performance estimates. So interestingly, here we pick the final model based on our empirical performance on the test data, which is usually a strict no-go in machine learning, I would say, but we do it anyways and adjust for the over-optimism. So in order to validate this procedure, this proposal, we conducted many numerical experiments, a huge simulation study where we basically repeated this whole machine learning pipeline of learning and evaluation multiple thousand times and compared the default procedure, which I initially described, pick the best model only for evaluation, and our proposal, pick multiple promising models. So what can be observed is that on average, we end up with a better model. So this is not the empirical performance, it's the true generalization performance, which we have a sort of additional test set, which is of course not inflicting our model selection, but we use for the assessment of this true performance gain. And additionally, we are able to limit false positives findings, just as we are in the one model case. And additionally, we can increase the probability to correctly identify a good prediction model, which is related to the concept of statistical power. All right, so our conclusion is, when in doubt, concerning the model selection, which is often the case in applications like medical testing where we don't have too much data, we should delay this final model selection to the test data, actually, with the before mentioned benefits. And I'm very happy to take your questions either after the session here or in the evening. Poster number 123. Thank you.
Thank you very much.
My name is Kush Varshni. I'm a researcher with IBM Research. I manage one of the machine learning groups in our Foundations of Trusted AI department. So the title is Topological Data Analysis of Decision Boundaries with Application to Model Selection. This is joint work with Karthikeyan Natesan Ramamurthy and Krishnan Modi. So what is topology for anyone who is not aware? So it's the study of shape, the mathematical study of shape. And one of the main topics that is looked at is understanding how many and what sorts of connected components, as well as holes or cavities of various dimensions exist. The image that you see is a classic sort of joke about topologists, that they see coffee mugs and donuts as exactly the same thing because they have the same topology, right? So specifically, a Betti number is used to denote the number of k-dimensional holes that is in a particular shape. So they go Betti 0 up to whatever dimension that you're in. So a circle, for example, has a Betti 0 of 1, Betti 1 of 1, and the rest are zeros because it's one single thing with one one-dimensional hole. Right, torus has 1, 2, 1, and then all zeros because, first of all, it is a single connected component. It has two holes, one through the middle and one that's the interior cavity that exists. The cross-section, and then the interior cavity is the Betti 2. Right? So statistics of Betti numbers characterize topological complexity. And when we're working with data, we actually don't have that shape. So what we're trying to do is analyze the shape of structures from which point clouds of data are sampled. A technique for doing this is called persistent homology, which is tools to recover those Betti numbers from data point clouds. They construct complexes at different scales and see which ones persist across those scales. So connecting data points that are close together and seeing whether they stick around and what shape they form, and we report Betti numbers for those. Okay. So this is all great. This is theory that's been being developed over many years, but it's all been for unlabeled data, and this is a supervised classification session, so what we usually have is labeled data, right? So as we're doing classification, what is the most interesting structure that exists? It's the decision boundary. And in this work, we propose to characterize the topology of the decision boundary by extending what we mean by persistent homology, and specifically trying to look at the decision boundary by connecting data points of opposite class labels. And then, because that actually doesn't do enough, we then complete simplices by doing length 2 graph walks. And that leads us to what's called a labeled Vietoris-Rips complex, and we can analyze that. One extra thing in the paper relates to local scaling, because when we are connecting data points that are close together, if you have different parts of the space in which the boundary has different scales, it actually doesn't work so well. So we are looking at that as well. And the application that we look at in the paper is with model marketplaces. So we've already heard earlier about buying and selling data, but we're also entering a world in which models themselves, pre-trained models, are being bought and sold. And it will very much be the case that vendors will be unwilling to let users download their model for free trials, and also consumers are unwilling to send their data to be tested to the vendor as well. So we still need to do some sort of matching to figure out which model is appropriate for which data set. And what we propose here is to match on the topological complexity of the model and the data set to see which ones might possibly work well together. So this is a complicated figure, but let me try to explain. The end result, though, is that, yes, using topological complexity is a good way to match models and data sets. So what we did for 3 10-class problems, we created different binary problems. So if there's 10 classes, you can have 45 different binary classification tasks, looking at each of 2 data sets together. And we looked at if you have a difference of performance of the 5 closest data sets to the model and the 5 furthest data sets in terms of topological complexity, do they actually have good and bad performance, which they do. So the difference in accuracy among good and bad models is actually significant. So what else is in the paper? We have a lot of theoretical results on labeled check complexes, which is a more theoretical construct in topological data analysis. And come see me this evening for poster number 124. Thank you.
Hey everyone, I'm Wan. I'm going to talk about contextual memory trees today. This is joint work with Elena from Yahoo Research, Hao, Paul, and John from Microsoft. So the high-level idea of this talk is that we want to build an external memory that potentially could be used for helping existing machine learning methods. In high level, it operates in an online fashion. Every round, given a query, for instance, an English sentence that is going to be translated to a Chinese sentence, for instance, this query goes into this external memory, and the external memory potentially could return an answer, right? A potential translation. And it could also potentially return a K memories, which are basically K pairs of English and Chinese sentences that could be further used by an existing inference algorithm or a machine learning algorithm, right? And then these external learning algorithm takes this K memories as input and outputs another answer. And the last component of this whole process is potentially a user who is evaluating the memory that you returned, right? It gives you a reward indicating how relevant and how good it is. And potentially a ground truth value for the current query, right? And with these 2 pieces of information, we're gonna close the loop by doing insertion and reinforcement learning. Insertion means that I want to insert this latest experience into my memory store, and reinforcement learning means that I want to update my external memory using the reward signal that I just got from the user, all right? So let's take a look what the desired properties that we want for such kind of system, right? First, we want it to be online, in a sense that every operation should work 1 example at a time, and all these examples should come in 1 by 1 in an online fashion. And 2, we want to have linear space, right? In terms of the number of examples stored so far, and we want it to be fast. In other words, we want operations such as read and write to be logarithmic with respect to the size of the current memory tree, for instance, or the size of the current memory store. And we want it to be learning-based, in a sense that we do not want to pre-assume some distance metrics, such as Euclidean distance, for instance. Right? And we want to be self-consistent, in a sense that if this external memory sees something that it has seen before, we want to just identify and retrieve it. Okay? So in high level, this contextual memory tree works as follows. So in this talk, we're going to define this memory as a pair of query and a value. Okay? And given the query, it has some function called query that takes this Q as input and then outputs a K memories. Okay? And then if a user provides some reward for some memories, then you can use this reward to perform an update using this function called update. Okay? And then if the user again provides some ground truth value for this corresponding query, then we can call this function insert to perform an insertion. Okay? So now I'm going to explain these 3 functions 1 by 1. So first, data structure. So basically, we're going to maintain a nearly balanced binary tree, right? So this whole system, this whole memory system is a binary tree, right? Nearly balanced binary tree. And this tree has 2 kinds of nodes. And an internal node, which is blue here, basically contains two numbers, NL and NR, basically indicating the number of memories that's stored in the left subtree and the right subtree beneath this particular node. Okay? And each node also contains a router. Here you can think about it as a binary classifier that takes a query as input and outputs -1 or +1. Okay? So -1 means that you should go left, and the +1 means you should go right. Okay? And there is another type of node, which is leaf, green here. So each leaf basically gonna store memories. Right? And we're gonna make sure that each leaf only store at most logarithmically many memories with respect to the total memories stored in this system. Okay? And all the leaves gonna share a score function that basically takes a query and a potential memory as the input and outputs a number sort of indicating how relevant this memory is with respect to the current query. Okay? Now with this kind of binary structure, we can do query. So basically a queue comes in and we're gonna use the router's prediction to route this example, right? For instance, if the loop predicts that for this query, it predicts negative value, then we should go left. And F2 predicts it's positive, then we go left, we go right. And when we get to leaf, we're gonna use this score function to pick up the most relevant memory from that leaf, okay? So now let's talk about how we update routers. So we wanna use reward signals to update routers in a reinforcement learning fashion, okay? So now you can think about, so let's fix the prediction, fix the routers. So now you can sort of think this routers as a policy, and given a query, it basically induces a pass where this query will be passed along, right? And given such a pass, we can basically randomly sample a node along that pass for update. For instance, in this example, we have this query queue, and we decide to update F2, okay? So how are we gonna do it? So in the ideal case, let's assume that you can, given a query, you can query the user for rewards twice, right? So the naive thing you could do is that you just first route this example to the left subtree. You get a reward signal from the user, and then you reset the system and route this example to the right subtree, and you get another value, okay? So now you're just gonna create a binary classification example where the feature is essentially the feature of the query, and the label is essentially the sign of the difference between the reward from the right subtree and the reward from left subtree, right? And then you feed this binary classification example to this F2 and perform an online update. So you're sort of encouraging this router to route this query to a site that contains higher reward, right? But in the reality, you might only get one chance to ask a reward for a particular query, right? So what we're gonna do in this case? So we're just gonna use a very simple exploration method, which is the epsilon greedy here. So we're just gonna flip a coin, and let's see with probability P, you just route this example to the right subtree, right? And then we're gonna use importance weighting to get an unbiased estimate of the difference between these two rewards, right? And then we continue by building this binary classification example. So far so good, but one issue here is that such kind of update procedure does not really guarantee that you can get a nearly balanced tree, right? Remember, this is gonna be extremely important because we don't want the tree to be, too unbalanced, right? Because that's gonna make the logarithmic computation impossible. So by encourage balance, we're gonna add a very special regularization when we're building this binary classification example. So what we're gonna do is to add this regularization term, which is log of the ratio between number of examples in the left subtree over number of examples in the right subtree. Right? So let's look at one extreme case for this regularization, which is the number of examples in the left subtree is way larger than the number of examples in the right subtree. Right? So in this case, the log of this ratio is going to be positive infinity, and then after you take the sign, the label going to be +1. Right? So this sort of makes sense because we are sort of encouraging this router to route more examples to the right subtree, which has less memories as so far, right? To encourage balance. So now let's talk about insertion. So as I mentioned before, one key property that we want is self-consistent. In a sense that if I see this memory M before, and next round I see the same query Q, right? I want to just route the query to this particular memory that I've seen before and just retrieve it, right? If a query I've seen before, I just want to get it. So how can we encourage self-consistency? So every time when we do insertion, we basically gonna train the classifier as follows. So let's say we have a memory and we insert it to this right bottom leaf. And along the way, we're gonna focus on training, online updating each routers. For instance, let's focus on this one. And we're gonna enhance its prediction by creating another binary classification example, but using the router's current prediction. In a sense that if the router predicts for this example that you should go right, then we want to enhance this prediction. So you sort of can imagine each router, if each router is some margin-based classifier, you're sort of increasing the margin a little bit for this particular example, right? And again, we add regularization term to guarantee balance. Right? So now, one issue is that this whole system is running online, right? We are updating routers every time, and routers, and that may result in lack of self-consistency. Because for the examples that inserted before, right? Because all the examples inserted before, they inserted based on the routers that are kind of out of dated. Right? So to fix that problem, we're gonna do experience replay. So basically, we're gonna random sample a memory, and we're gonna delete that memory, and it's traced in the tree, and then we're gonna reinsert it using the latest routers. Okay? And we're gonna apply this replay constant times per insertion, per example. And now let's talk about some empirical results. So we first evaluated on extreme multi-class classification problem, where the memory is essentially a pair of feature and label, and we use 0-1 loss as sort of the cost signal, the reward signal, okay? And then the second task is extreme multi-label classification, where a memory is a pair of a feature and a set of labels. And we're using Hamming loss as the cost signal. And the last one is some image retrieval task, where the memory is a pair of captions and image. And we use the similarities between images as the reward signal. So we first test the online progressive performance of contextual memory tree on extreme multi-class classification problem. Right? So we consider two data sets. The first one has 1K classes and 100K examples. The second one is much harder. We call it 3-shot. Meaning that you have 10K classes and 30K examples, meaning you only have 3 examples per class, right? So generalization could be really hard in this case. So extreme here means that you have very few number of examples per class, right? So generalization might be very hard in this case. So nevertheless, we compare it against 3 baselines. They're all designed for multi-class classification. The 2 of them are basically long tree, and record tree. They're designed for achieving logarithmic inference time for multi-class classification, logarithmic with respect to the total number of labels, total number of classes. And the last one is the very classic and common one against all. Right? But the inference time is linear with respect to the number of labels. So as we can see in these 2 plots, the contextual memory tree basically outperforms all these 3 baselines, especially at the early stage when we don't have that much data. Right, so the second experiment, we're trying to see if we can use contextual memory tree to help some existing external inference algorithm, such as 1 against all, for instance, okay? And we consider 3 data sets that has a lot of labels, right? So here, extreme means you have very large number of labels, so linear inference time in terms of number of labels, it will consider to be slow, okay? So the whole pipeline is like this. So I have a query queue, and I feed it to the contextual memory tree, and then it returns k, a small case, k is a small number, k memories. And then this external inference algorithm, 1 against all, just gonna look at the subset of the labels that were induced from this k returned memories, right? So instead of looking at all possible labels, do 1 against all, I'm just gonna focusing on this potential labels returned by the memory tree, right? And in terms of performance, as we can see, for larger data sets, in terms of computation, CMT is faster in terms of both inference time and training time. And for statistical performance, it basically is similar to 1 against all, but sometimes could even be better. So the last experiment that we tried is to compared to a naive nearest neighbor approach. So here, a query is some feature of captions, and then the value is some feature of an image. Okay? And as we can see here, CMT is basically much faster than a naive nearest neighbor in terms of inference time. So here, CMTU stands for an unsupervised version, where we just turn off the scoring or learning function at the leaf level, and whenever an example gets to a leaf, we just run nearest neighbor, right? But recall that we only have logarithmic many examples in a leaf, so doing a nearest neighbor in a particular leaf is basically much faster. So we also did some evaluation task. So the first question that we want to answer is, empirically, how does the computation scale with respect to the size of the memory tree, right? So you said, it scales logarithmic time, but is it true? So we basically run CMT on a data set of which the size increases from 1K to 100K. And from this plot, we can basically see that the inference time increased logarithmically with respect to the size of the memory tree, rather than linearly, right? And then what about self-consistency? So to test that, we create a one-shot data set. One-shot here means that you only have one example per label, right? And which basically means, the training error in this data set is equal to the probability of, missing yourself, right? The chance of not being self-consistent. And zero training error here means perfect self-consistency, right? As we can see here, as the learning procedure goes on, this self-consistency consistently improves, right? Meaning the training error pretty much converges to zero. And the last question is, how does the performance scale with respect to the classification difficulty, right? So here, we create a series of data sets, which we call it Alloy S-shot. So here, S means number of examples per class. So we increase S from 1 to 100. When S is small, it means that generalization is going to be really hard, right? Because we have very few examples per class. So we compare to recall tree again here. And as we can see that both approach, they basically improve when the data set's getting easier, when S getting bigger, right? But CMT basically can significantly outperform the recall tree when S is small, meaning on data sets where generalization could be potentially really hard. So now let's revisit our desired goals, right? So we achieve online by just doing reduction to online classification, right? Every router is basically a reduction to online classification. And then linear space, we basically store examples in the leaf, and we make sure that we only have n over log n many nodes, many routers, where n is the total number of examples in the tree so far. And then we ensure logarithmic time by adding this special regularization term. We can prove that this is a near balanced binary tree, okay? And then it's learning-based because we are sort of doing this reinforcement learning type of update for router. And it's self-consistency in an asymptotic perspective due to the existence of experience replay. So last but not least, CMT is already in the latest release of Vorbit, and I encourage you guys to try out. That's it. Thank you.
All right, I'll present the paper Sparse Extreme Multilabel Learning with Oracle property on behalf of the authors. The authors unfortunately didn't get the visa, and I didn't know that until last night. I have to present the paper, so please direct all the questions to the original authors. They studied the problem of extreme multi-label classification where each data item could be associated with a lot of labels. So it could be formulated as a multi-output regression problem, linear or non-linear, but the extremely large number of labels will cause challenges and will require us to use some Parnassus regularizations to regularize the solution space. One classical method in this prior literature is called SLEEK, short for sparse local embeddings for extreme classification. It aims to learn a small example of local distance preserving embeddings and has been very successful since it's been proposed in 2015. So this paper primarily wanted to answer some theoretical questions which was traditionally not answered for this method. They first tried to see how to extend the SLEEK with more non-convex non-linear operators, and also they tried, the most important part of this paper is to establish the statistical rate of convergence and Oracle property of SLEEK while remaining the good predictive performance. So the author studied the form of a proposed estimator in a relatively simple linear prediction problem. So they want to solve this V star, which represents a non-sparse regression coefficient matrix, and the W is a noise. So it's a typical multilinear regression problem. And they also propose to estimate this V star by minimizing this objective consisting of a fidelity term, typical for regression, and also a regularization term for the magnitude of the V, plus non-convex regularizer, additional non-convex regularizer for V. The key point about this V is it has to be decomposable, but in addition to that it also reveals the requirement on the V could actually be quite relaxed. The many non-convex penalty functions, such as the clipping method, gradient penalty, and my-max concave property, all having the potential to be incorporated into the framework, but the author discuss on two primary categories: the smoothly clipped absolute deviation scat and the min-max concave penalty in that. But they did mention in that paper it could be extended to more. So the main result of this paper include two theories, and theorem one is stated. Well, they didn't do comprehensive inclusion of the preconditions, but according to their original paper, they assume that if the non-convex penalty function would satisfy three regularity conditions. I remember the three conditions are: first, the function and the derivative have to both pass the origin point. Second, the derivative have to decay beyond a certain decay to zero, passing a certain threshold. And third, the derivative has to be monotonical and ellipsis continuous. So it's certainly some requirement, but not that hard to be satisfied. As long as the three conditions are met, we could have a quite nice property of the proposed slick framework with non-convex regularizers that it is identical to the Oracle estimator under those conditions. So that means we know in the model beforehand or not, the model will theoretically perform as well as it knows the model already. So this is a very strong result and haven't been established in previous literature more. So, okay, so first one is the achievability problem. So we already established there is an Oracle property, and the next one we wanted to know how fast, how efficiently we could achieve that good Oracle. That leads us to the second theorem, which discusses desirable statistical convergence for estimating this V star. So looking at this theory, in plain language, the theory means that we could not only we could achieve that good result, we could achieve that in quite a good sharp convergence rate as well. So I will, due to time, I will avoid explaining too much in details. I have included the full proof. So they have done the precision and the NDCG result in a few small size simulation dataset and 3 medium size dataset in the text classification literature. And of course, they show that the numerical results are better than all the results compiled here. And if you're interested in the work, please come. So here are the conclusions, just to reiterate, and please come to the poster, which will be hanging there tonight. Thank you.
Good afternoon. I'm Tao Zhu from Google. I'm here presenting our work on shape constraints for set functions. This is joint work with Andy, Maya, Heinrich, Irez, Jim, Taman, and Srinath, all of which from Google. So we're dealing with the supervised learning problem of, say, predict a label given a very precise set of feature vectors. So one example of this problem is that to classify a recipe given a set of ingredients. So another common type of use case in which the input is not naturally in the form of a set, but it's a kind of sparse categorical feature that can be broken into a set of items. So an example is the Kaggle Kickstarter problem, say, predicting if a campaign will succeed given its name. So now, given the name superhero teddy bear, if we have seen that name enough times in the data, we can easily get a good estimation of the expected value of the label, and we're done. But chances are such a unique name is not that common, and we may have never seen that before. So what we can do is that we can break that into a set of meaningful n-grams, and we can get a good estimate for each of them because they appear more frequently. And then we apply some kind of predefined simple set functions to estimate the label. So now to make it a little bit more flexible, what we observe is that the term superhero appears much more frequently than teddy bear, so we should weight more. So we can use the weighted mean to capture this, and we'll keep going and adding more features to the weights. So now this kind of predefined simple set functions are nice and simple, and we know exactly what they're doing, and they work surprisingly well in a lot of use cases. But still, they feel a little bit inflexible and suboptimal, especially when the problem gets more complex. So a natural solution in this case is to discriminatively learn such a set function. So a recent research on deep sets in NeurIPS 2017 showed that all set functions on countable sets can be expressed by a formula in certain form, which suggests that by building deep neural nets following a certain architecture, we can probably achieve the possibly greatest flexibility when trying to learn these kind of set functions. But then we run into the risk of the model being too flexible and overfits the data. And what's more, we now lose the nice feature of the set function being easy to understand. So now taking a step back, we're trying to find out what makes a set function such as the weighted mean so easy to understand. So we found that they satisfy certain properties that captures certain domain knowledge about the input features. For example, the output of weighted mean can only increase if the score of each input increases. Also, we found that in a weighted mean, there's some other kind of auxiliary features that conditions the primary feature and tell us how much we should trust that. Also, we found that these kind of properties exist not only in this type of use cases, but in other types of use cases as well, including normal functions that are not set functions. So the question is, can we learn set functions that are flexible but still capture these kind of properties for more regularization and better interpretability? So our answer to this problem is to use what we call deep lattice network with shape constraints. So without going into too many details, so the basic idea is that we build a 6-layer model using layers which are parameterized in such a way that allows us to express these kind of shape constraints using linear inequalities on the model parameters. So we call them shape constraints because they restricts the shape of the functions. And then we jointly train all the parameters in the model by solving the constraint empirical risk minimization problem using algorithms built on top of SGD. And using these kind of layers, we prove that the same shape constraints can also work for normal functions as well. And on top of that, we propose a general nonlinear strategy for estimating a label given a sparse categorical feature, what we call semantic feature engine, because the output of these estimates, they can be used as features in another machine learning model. And then we inject similar domain knowledge about the features using shape constraints. The results show that we achieve similar accuracy as deep sets and deep neural networks with a learned embedding on the sparse feature, but with guarantees on the model behavior. So for more details about our work, please come to our poster number 127 tonight. Thank you.
My name is Guy Cohen, and I'm about to present a joint work with my advisor, Professor Daphne Weinshell from the Hebrew University, about curriculum learning in deep neural networks. So teaching is a hard problem, and when we teach human subjects, we usually use a curriculum. So what curriculum does, it's break down the problem into tasks and let us teach simple concepts before some other ones, under the assumption that complex concepts are composed from simpler ones, so learning the easier ones first will be beneficial. So this kind of learning is widely used in humans and in several machine learning paradigms, and we would like to introduce it into deep learning. So in deep learning, we can think about the neural network as a student and the learning algorithm as the teacher. And the goal of the teacher would be to teach the classification data to the network. And traditionally, the data is sampled uniformly when doing that. So this is correspond to a teacher just sampling randomly examples and showing them to the students, which does not make much sense in humans, so maybe it also does not make much sense in neural networks. So our idea is to create some better distribution to sample the examples from and show them to the network in maybe a smarter order. So in order to do that, we decompose the problem into two parts. The first one is to define a scoring function, which is essentially taking the data and deciding how hard each example in the data is, so we can compare between them and show the easier one first. And since we are using here visual data, this boils down to the question of giving an image how hard to classify the image is. So in some cases, this is a very easy task to do. But in the general case, there is no clear answer of which images are there, so not even for humans, and let alone for neural networks. Another function that we defined is a pacing function. So it's not enough that we know how hard each example is. We also need to know how fast we should introduce new concepts to the learner. If we do it too slowly, the learner might get bored and won't learn anything. And if we do it too fast, we might overwhelm it and miss out the point of the curriculum altogether. So in our paper, we tried several scoring and pacing techniques, but I'm going to focus here, due to lack of time, on just a specific scoring function. So one of the scoring functions was a curriculum by transfer, and the idea of it was to determine the hardness of each example by the performance of some stronger model on it. So what we did was to take the inception model and train it on ImageNet, which is a much larger dataset than the dataset that we used, and then take the one before last layer of it and train some linear classifier on that layer, and use the confidence score of it to determine how hard each example is. And when we do that, then we can see these results. So in the x-axis here, we see the number of learning iterations. And on the y-axis, we see the test accuracy. And we can see that using the curriculum speeds up the learning. So in every time point, the accuracy of the curriculum is better than without any curriculum. And it's also reach a better final solution. And in our work, we also include some theoretical and empirical analysis of that, and try to explain how exactly curriculum affects the objective function of neural networks and why it might lead it to some better minima. But if you want to hear more about that, then please come to my poster, number 128, and thank you.
Hello, my name is Vladislav Polyansky. I'm from KTH Royal Institute of Technology, and together with Florian Pokorny, we developed this Voronoi boundary classification algorithm. So what is a Voronoi diagram? It's a way to split the space into cells where within each cell we have points that are closest to some particular point from our data set. And if we look at the most classical way of classify the data, it can be seen like we can look at one nearest neighbor classifier, which can be seen as testing of the membership in the Voronoi cell. And our algorithm kind of builds up on this idea, expands it, and preserves the intuitivity and geometricality of the method. So let's start with the toy example. We have points of two classes, and we are given this point in black, which we need to classify. And our approach is based on the idea that we look at the decision, we are looking at the boundaries of Voronoi cell of that point, and we compute the weighted volume of that of the boundaries related to specific classes. And each point of the boundary is weighted respectively to the distance to our test point. And we say that, and we call those integrals Voronoi boundary ranks, which are related to each of them to the specific class. And in order to weight, we introduce this function, which is controlled by the alpha parameter. The alpha controls the peakiness of our weight function. So in this case, for two-dimensional data or for three-dimensional data, we can just compute these integrals explicitly, just by constructing the Voronoi diagram. But whenever we go to a high-dimensional space, when the dimensions is like above 5, and we have a reasonable size of data, then the computational Voronoi diagram is infeasible. Thus, we use a Monte Carlo approach to approximate the integrals. So in order to do the Monte Carlo sampling, we need to change the domain of integration. That means that because the initial domain of integration is our Voronoi CL boundary, which we don't have. Thus, we use this change of integration domain formula to switch from the boundary to a hypersphere. And this integration can be seen as the way of casting rays from our test point in uniform directions. And for each ray, we just need the distance until this ray hits the boundary and the normal vector at the point of intersection, which could be obtained quite easily. So now we can move to more practical results. So this is just a simple example how a decision boundary would look like for this toy case and arbitrarily picked weight function with the arbitrarily picked parameter. However, if we change the pickiness of the weight function, we can, on one end, with a very picky function, we get an approximation of one nearest neighbor classifier, as seen on the left, and on the right, when the function is more constant-like, we get the classifier that just looks at the pure volumes of Voronoi boundaries. But again, this is all toy 2D cases. We, in our paper, show that our integration method converges really well, even in very high-dimensional data. And for example, we test our algorithm with on-MNIST and CFAR, which have thousands of dimensions, and test the classification results with other classical non-parametric methods of classification. And our method, which is the first in this line, it obtains the results that are on par with random forests for this data. However, our algorithm doesn't require any training. It works with unbalanced data, and it kind of expands one nearest neighbor in a way that it uses more information about the geometry of everything, of the Voronoi diagrams. And we also show that accuracy converges really quickly within a few thousand of iterations of samplings. The accuracy converges to a fixed value. So if you are interested in learning more, you can come to this poster, and I will answer questions. Thank you.
Thank you.